IP multicast. Now, IP multicast is one-to-many traffic delivery where we have one source of the traffic sending a single copy of traffic that the network itself is going to deliver to multiple clients, but only to those clients that have actually expressed the wish to receive this traffic. Now, IP multicast is a concept, or I would say not necessarily IP multicast, but multicast traffic delivery is something that sits between unicast and broadcast. Now, broadcast is of course one to all, and unicast is of course one-to-one communication. Now, multicast is one to many. So everything that we talked about during this course this week was dealing mostly with unicast traffic. How do we get traffic from one source to other? How do we learn the routes? What are the challenges there and how do we solve? Now, broadcast and multicast share some common problems, some common challenges, and I'm going to explore that. Now, I should point out that there is no such thing as network-wide broadcast. There is only network-wide multicast. Broadcast is usually contained to single network segments, to broadcast domains. But nevertheless, before we can actually talk about the multicast, this one-to-many, before we can talk to one-to-many, to where we are talking about, okay, I want to deliver traffic here, but not to these guys here. That itself is a challenge especially, but there is also a challenge in delivering the traffic from one to everyone. So in order to see how multicast works, we actually need to understand what is the challenge in delivering the traffic from one source to multiple destinations in our network. Now, to explore that, I'm going to use a relatively simple, straightforward network that doesn't contain any redundancies or any complicated paths between them, and it's relatively small. So this is the network that I am going to be dealing with. Now, as you can see here, in this network here, we have one source, and let's see what needs to happen in this network here to deliver the traffic from this source to every single node in this network. Now, I have multiple possible options here. Now, one of the options that I could do here is I can send the traffic from source to R1, then I can send the traffic from source to R2, then I can do the same thing for R3, then I can send traffic for R4, then I can send traffic to R5, R6, R7, R8, let's say then to R9 here, and then we send to, for example, R10. Now, at this moment, I have actually solved the problem of sending the traffic to every single node here, but I also have created another problem. This interface here now needs to send 10 copies of this traffic. Now, if this was high volume, high bandwidth traffic, there could have been a saturation here. So this here would be sending unicast traffic to multiple destinations. Now, in some cases, this works like a charm. For example, if this was here, for example, YouTube, this is exactly what we would have. If these were viewers of YouTube stream, they would all be getting a separate copy of YouTube. But then again, you need to be Google to have a lot of bandwidth available to you. Now, not all of us are Google, so sometimes we might actually need to find a little bit more efficient way of delivering this traffic from a single source to multiple clients. So let's now see what would happen if our network here would implement a relatively simple flooding rule. Let's say that we send the traffic from the source to our network, and that there is a rule here on R1, replicate the traffic received here out of all interfaces except the interface on which you received this traffic on. So if this is the case, we would have this. Now, there is going to be some backplane use problem here, but it depends on the implementation of this replication on the device itself, whether this is going to be a problem or not. But network-wide, we at this moment don't have the problem. So let's see what could happen next. So now R2 here could have the same replication in place, and let's say we deliver the traffic here, we deliver the traffic here, and we deliver the traffic here. But we're also going to send the traffic to R4. Now, R4 already has a copy of traffic from R1 and replicates the traffic to R2, replicates the traffic here, sends the traffic here, and sends the traffic here. But R4 also received this copy of traffic here, so it sends it here, sends it here, sends it here, and sends it here. Now, our R2 has this copy of traffic, so it replicates that traffic. This goes to R1. Now, R1 has the copy of this traffic, and you get the idea. Very, very soon, this here is going to turn into one gigantic loop. Now, we're going to have the same problem here throughout the network. Now, this precise scenario is what happens, for example, in our layer 2 networks, in our switched networks, when we don't run things like spanning tree. Now, you might remember that we had one example earlier when I talked about layer 2 networks, when I talk about switch networks, when we had two switches that had two links in between them, and we turned off spanning tree on those interfaces using BPDU filter, how fast the traffic started multiplying, because it was an uncontrolled replication of traffic, uncontrolled flooding. So this is the result. This is exactly the same thing that we are going to hear if we implement a very, very simple, uncontrolled replication of traffic. If we simply take the traffic from an interface and then fan it out to everywhere else. Now, what we need to do here is we need to have some level of control of where we actually replicate this traffic. Or not where we replicate it, but where we replicate it from. Now, what we want here, our ultimate goal in this task, is to have the traffic flow from the source onwards. So we do not want here traffic to ever go back towards the source. What we want to do is we always want to send traffic from the source. Now imagine that this was, for example, a river, and that this was a hill or a mountain. When you have a mountain, you have a river that flows on it. It will always flow down the hill. You're never going to have the river that flows up the hill or up the mountain. Now, it might go just a little bit up, but in grand scheme of things, the water will always flow downstream. It will always flow down as the result of having gravity. Now, obviously, tilting our routers a little bit, let's say putting R1 here and R1 is not really going to help, because gravity is really not a factor here. But we need to find some way to artificially make the routers flow from source onwards and never go back towards the source. And in this one-to-many replication here, we actually do have a mechanism that does that. So when the source sends the traffic here, now this is IP multicast traffic in our case, or it could be network-wide broadcast, whatever it is, but this is going to be IP traffic, and it is going to have some source IP address. Now, this source IP address is the IP address of an interface on the source that actually generates this traffic. So this traffic now arrives to R1. Now, what R1 is going to do before it blindly replicates this traffic, it's going to ask a simple question. If I was thinking about sending unicast traffic towards the source, would this be the interface that I would be using to send this traffic from? Is this the best path to reach the source? Now, mind you, I'm not at all looking at what the destination of the original traffic was. I'm looking at the source of the traffic. Now, if the answer to this question is yes, in that case, we are actually going to replicate this traffic. Now, this question here is something that is called the RPF question, or the reverse path forwarding. Now, what do we mean by reverse path forwarding? Well, what we mean by that is that multicast traffic, or this network-wide broadcast that I'm just inventing that doesn't exist, is going to flow in the exact, from the source towards the destination. Let's say that this is the destination, one of the destinations, is going to flow towards its destination in the exact same path that traffic from destination would take to source if it was unicast traffic sent from R10 to source. So if I had the unicast traffic from R10 that would follow the routing tables on these routers and going in this direction here, so if this was unicast traffic, my multicast traffic from source to destination will actually flow in the exact same path, in the opposite direction. So this is going to be multicast. By default. So this is going to be the default behavior. This is why we call it the reverse path forwarding. This is what this simple check here accomplishes. Is this interface the best interface to send this unicast traffic? If the answer is yes, we say that RPF here has succeeded and the replication can actually happen. Now, let's declare this interface here, this interface here, this interface here, this one here, this one here, this one here, and this one here as the best interfaces in our case. So if this is indeed true, what will happen? We are missing one on R4, so let's say that this one is the best. So what would happen when this traffic arrives to R1? Our RPF actually does succeed here, and the traffic gets replicated here, gets replicated here, gets replicated here, and gets replicated here. Now, on R4, we are receiving two copies of traffic, one that does arrive on interface that, for whatever reason, is the best. This traffic here is actually going to be dropped, but this traffic from this interface will be replicated here, will be replicated here. Unfortunately, this traffic will actually be returned here. But because this is the RPF interface, this gets blocked here, and in multicast there is actually a solution for this problem that we have sent two streams that are exactly the same. It's called something, it's a feature that is called PIM assert. So PIM assert, I'll talk about it a little bit later on, is something that will actually take care of this problem. But as the result we are going to have here, what we are going to have eventually is a loop-free delivery of traffic towards all the routers in our network. So we might have this temporary multiplication of traffic on single links, but we are not going to have that endless loop. So what we are going to have in the end, in the result, is that we have delivered the traffic. Let's say that these were the actual paths that were used. We would have delivered the traffic to all nodes in our network in a relatively loop-free fashion. So that simple verification, that simple RPF allowed us to have not an uncontrolled replication of our traffic, but to have the controlled replication, the controlled flooding. So we are not going to flood all the traffic, only the traffic that is flowing from the stream, from the source of the stream down. This is how traffic from source will be delivered everywhere else. But what if we had a situation where we didn't want to deliver traffic everywhere, but we actually had a client that was interested in actually receiving this traffic. So here is our client. Let me add this network here. So let me just move it a little bit here, like so. So what if we had actually, you know what, let me just start a new page here. So what if we had a client here on R10 that wanted to receive the copy of this traffic? So this is the only client. Now I might have multiple clients, but if I send the traffic and if I flood it throughout the network and deliver it to every single node in our network, and let's say that this here is the best path to deliver this traffic, is there any need to have that traffic on these nodes here? Now, what I have just shown you is the network-wide broadcast, but what I need really is just this path here. No one else in our network actually needs to know that there is this traffic. Only these nodes, R1, R4, R8, and R10, because if this is the best path, this is where I want to deliver this traffic. All these other routers here really didn't need to have a copy of this traffic. This is where the multicast actually comes into play. Now, with multicast, when we are sending this traffic, of course, this traffic will have a source IP address, and this would be an IP of a sending interface. We are also going to have a destination IP address. Now, this is going to be a group IP address. Now, multicast traffic is identified by multicast groups. Now, multicast group is a fancy name for an IP address. Now, if we have a traffic that is sent to any of the IP addresses in this range, we know that this is multicast traffic because this is a reserved range for multicast. So it is from 224.0.0.0 to 255.255.255. So this is the valid range of multicast addresses. Now, one thing that is very, very important, that source here, the only capability of the source is the only capability, or I should say the only requirement, is the ability to send IP traffic. Now, what I mean by that, if this source can send IP traffic to one of these addresses, it is actually considered to be a multicast source. There is no signaling between this source and this router. The source does not actually participate in IP multicast. The only thing it does, it simply generates the traffic. This is very, very important. Now, of these groups here, there are some groups that actually do have special meaning. Now, these are the groups that actually do have special meaning. So 224.0.0.0/24, this network, or this range of multicast groups, I shouldn't say this network, but this range of multicast groups from 224.0.0.0 to 224.0.0.255 is considered to be link local multicast. Now, this means that this traffic will never be routed. No routers will ever route this traffic. They can send and process the packets to and from this destination, but they will never actually take them on one interface and route this traffic out of another interface. The reason is because this is link local. It's a reserved range for link local multicast. On the completely other side of the spectrum are the addresses 239.0.0.0/8, which are private multicast addresses, or I should say private multicast groups. And I'm going to write here just so you know what I mean by that. These are equivalent of RFC 1918 addresses. Now, I'm going to put this under quotes because these are not actually defined in RFC 1918, but you can think of them that way. If you want to use multicast only in your organization and not route it outside your organization, you can use this range of groups and you are just fine. Now, here in between, all groups are treated pretty much the same way, except a couple of them. Now, one of those groups that is treated specially by default is 232.0.0.0/8, and this range of addresses from 232.0.0.0 to 232.255.255.255 are something that are called source-specific multicast addresses. Source-specific multicast, or SSM. So if you see a requirement to use addresses from this range, the task is basically telling you to implement source-specific multicast, and I will talk about it later on, but first I'm going to talk about any source multicast. Just what we consider to be regular multicast is actually ASM, or the any source multicast. And if you see source-specific multicast in your lab, be happy about it, because this is probably the simplest task you can have in the lab. Now, another special address, and this is a really fun one, is 233.0.0.0/8, and this is something called GLOP. Now, contrary to popular belief, GLOP doesn't actually stand for anything. The authors of this concept simply liked the name of pronouncing GLOP. So it's not an abbreviation, it's not an acronym, it doesn't stand for anything, it actually stands for GLOP. Now, what GLOP is, so I'm just quickly going to explain it here, is a way for organizations that have the autonomous system number to map it to multicast groups. So basically the way that works is if you have a 16-bit, so it doesn't work for 32-bit autonomous system numbers. If you have a 16-bit autonomous system number, let's say that your autonomous system number is 65,053, for example. So this is one of the private ones, so I'm just going to use that as an example. Basically, these here are 2 octets. So we have octet 1 and we have octet 2. And these 2 octets need to be mapped somehow to these 2 octets here in our 233 network. So we see here that we have 233.000/8. So each autonomous system number will actually get 256 multicast groups it can freely use on the internet by mapping this autonomous system number, these 16 bits mapping to these 8 bits here and these 8 bits here. This is the way it works. So the best way to actually convert this would be to use the calculator and use the autonomous system number. So here we have 65,053 and convert this into hex. So this is FE1D. So this is FE1D. Now this here is octet number 1 and this here is octet number 2. Now when we convert FE1D, so here I'm going to say FE1D, I'm going to convert, oh actually not, just FE, I'm sorry. FE converted to decimal, this is going to be 254. And octet number 2 is 1D, so this is 1D. When I convert it, it's going to be 29. So basically what I'm going to do here, because this is octet 1, this is going to go here, and this is going to go here. So basically, the GLOP range that I can use in my network is going to be 233.254.29.0/24. So I have these 256 groups available for use in my network. Now, is this important for the lab? It could be, because in the lab, they could tell you, use GLOP addresses for your routing, and if you had autonomous system assigned in your lab in the BGP task, you need to know how to get from the BGP autonomous system number, how to actually get the available list of groups. Now, mind you, I keep repeating, these are 256 available groups, which means that .0 here is perfectly valid group address, and so is 255. So this is very, very important thing, because another thing that they could tell you is use the second available GLOP group. And you might be thinking, okay, 0 is not used, so the first one will be 1 and the second one will be 2. So in your lab, you solve the task using 233.254.29.2. When instead you should have actually used .1, because this is the second available group. Because 0 here and 255 are perfectly valid. Remember, you have 256 multicast groups available for you. So these are some of the special groups that you need to be aware in the lab. As I said, these are the groups that actually do have some sort of special behavior associated with them. All other groups are just that, multicast groups. Now, there is one more range that is kind of significant, but it doesn't really have a special behavior on it. Now, this range is 224.010/24. Now, these are reserved addresses. That are assigned by IANA to different protocols. And one of the most significant addresses here, actually two of them, are 224.01.39 and 224.01.40. that are used by Cisco's Auto RP. And I will talk about this later on, but there is no special behavior about this group in particular, about this range of addresses, but there is some special behavior associated with these two. But I cannot talk about it right now. I will talk about it later on when I actually talk about Auto RP. I'll mention what is the special behavior about these two groups, but only on Cisco routers. So only on Cisco routers they are treated somehow differently than other groups. As far as all these other groups are concerned, they are just that, other groups. They do not actually have any special behavior associated with them. So going back to our example here, our source is now sending the traffic, and we want to deliver it only to those nodes that actually want to receive the traffic. So we know that source here, the only thing it needs to do is send the traffic. So there is no special requirement for this device. All it needs is the ability to actually send the traffic. So right now, when the source is transmitting the traffic, what is going to happen is the source IP address and the group IP address are a pair that is in multicast is called S, G. Now this S, G, and this is how it's written, is something that we call a multicast state. Now multicast state is also a multicast route. So when R1 here, the first hop router, actually receives this traffic, S, G state is going to get created on this router. And here I should point out that I am simplifying things a little bit. There are actually a couple more steps involved here. There is going to be one more temporary state, one transient state that gets created on R1, and you can actually see it with show IPM route. But that other state is a little bit irrelevant. I'll get back to it in a moment. But what is relevant on this router here is this S, G state. Now, what S here means, the S will actually be the source IP address of the source, and G will be the group address of the destination. So when we see this pair, when we have source and the group, we know that this router actually knows who transmits the traffic. Now, let's now take a look at what is happening on this side here. Now, the client C on this side wants to receive this traffic. So this client actually sends using protocol called IGMP, sends a request to router 10 telling it that it is interested in receiving traffic sent by any source to this group address. Now this state here is something that we call star, G. Now this star, G, technically speaking, exists on R1 as well, but that is that transient state that is not actually relevant on R1, because you cannot have S, G state without actually having star, G state. But as I say, this star, G is not actually relevant on R1. What is relevant is this S, G. However, on this router, on R10, our star, G state is actually relevant. So now on R10, we say that R10 now knows that there is a client here interested in receiving traffic sent to group G. Now, here we have the source that R1 knows about, and here we have a client C that R10 knows about. So how do we bring them together? Well, does R10 know who the source is? The answer is no, it does not. Neither does the client. Now, does R1 have any directly connected clients? The answer is no. There is a client behind R10, but does R1 know about this? The answer is no. And this is one of the biggest challenges in multicast. How do we make clients or routers that have clients find out about sources? And how do we deliver the traffic from the source sent to a particular group? How do we deliver that traffic to the clients that are actually interested in receiving this traffic? Now, there are two perfectly valid approaches about this, and that is that the router that knows about the clients should let everyone else know about it. That's one approach. And the other approach is that the router with the source should let everyone else know that the source actually exists. Now, people considerably smarter than me have decided that it's much, much more important information about the active source in our network than about clients that are interested in receiving some traffic. So it will be up to R1 to somehow communicate the presence of this source to R10. So this is where we are going to start talking about something that is called dense mode multicast. So dense mode multicast, oops, let me just correct that. I didn't see where the end of the whiteboard is. I'm just going to say dense mode. Now, we are still here talking about any source multicast. So this is not source specific solution. This is any source. Now, in dense mode multicast, the assumption in the network is that we have high density of clients. That means that we expect clients to be all over the place. So what is going to happen when R1 actually receives this traffic? It is going to, following those flooding rules that we learned before. So where is that picture? So following these flooding rules that we are going to send the traffic everywhere in relatively loop-free fashion, what's going to happen there is R1 is going to flood the traffic. So let's say that this traffic gets sent here, and the presence of this traffic on R2 actually creates S, G state on R2. Let's say that this traffic gets flooded here. The presence of this traffic creates S, G state. Then we send the traffic here. We create S, G. The traffic is sent here, creates S, G. Let's say that this was the best path. Then we create state here. The state gets created here as well. And finally, let's say that this guy delivers traffic here. And let's say that R8 sends the traffic here. Now, when this traffic actually arrives, so this is the actual traffic being sent. So whatever the source is being sent now is being flooded throughout the network. When it's being flooded throughout the network, as the traffic arrives, each router actually learns about the existence of the source that is transmitting to a particular group. Now, R10 has the traffic and it can actually deliver this traffic to the client. So the client is now happy. Now, the problem here is, of course, did we actually need this traffic anywhere in our network outside this path that I now decided is the best path? So I keep changing my mind about what the best path is. So do I need any of these routers here to know about the existence of this traffic? Well, the answer is not really. So what these routers can do now is the result of not having any downstream clients that are actually interested in receiving this traffic, or routers that they are aware that receive this traffic. These routers can tell these guys here to stop sending the traffic. So this is something that we are going to call the prune message. Now, the routers between themselves are going to be communicating using something that is called PIM, or the protocol independent multicast. So basically, this router is telling R4, hey, you know what? Don't send me this traffic. I don't need this traffic. Now, R4 here does have one interface that has the client. So R4 now says, okay, you know what? I'm not going to be sending you this traffic anymore. So it stops sending it here, but it keeps forwarding the traffic down this path. Now, the same thing happens on R9. R9 says R6 here, hey, you know what? Stop sending me this traffic. Now, R6 stops sending this traffic, and now R6 no longer has any downstream clients. So it basically says the same thing to R2. So now R2 stops sending this traffic. R3 sends the prune. This happens here. R5 sends the prune. And R2 sends the prune here. So basically, what we are going to end up is the situation, and this is going to now require some cleanup on my end. What we are going to have now, let me try to see how much damage I'm going to cause if I just simply delete this. Okay, so what we are going to end up here is that these routers here have these states and actually have the traffic, but these guys here don't have a copy of traffic anymore. But they do maintain the state. So these guys here have kept their states, but they don't have a copy of traffic anymore. So that prune message basically told the routers that were transmitting traffic to these nodes that they don't need it to stop sending them the traffic. So that traffic was unnecessary, but what we do have, we maintain the information about the states. Now, that means that if I had a source here, a rogue source, that would simply do a ping sweep on all the multicast addresses, I could basically crash all of my routers because of the number of states that I would create. This is why these states are actually temporary. There is going to be a 3-minute timeout after which these states are actually going to expire. So when this 3-minute timeout has kicked in, this state here is gone, this state here is gone, this state here is gone, 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 and gone. So only these routers here are going to maintain this state. So let's see what happens next. Let's say that this router here now gets the client that actually wants to receive the same traffic. So we send star comma G request. Does R7 here know who the source is? The answer is no. It doesn't know because it lost that information about the state. So what's going to actually happen? After these 3 minutes expire, the source or the first hop router, in our case R1, is actually going to re-flood the traffic. Now, why is it going to re-flood the traffic? So that we can reset the states, so that the states actually can be recreated in these routers in the case that the client actually shows up on them. So every 3 minutes we are going to have this flood, prune, as long as the source is actually transmitting. So every 3 minutes there is going to be this send, stop, send, stop, send, stop operation. But you know what? In your network, this might actually work. Now, here is where I'm going to do my emphasis thing. In my life, I had the pleasure on going through the multicast lecture delivered by a person called Bo Williamson. At that time, he was a Cisco employee and is the same person who wrote the book called Deploying IP Multicast Networks. Now, one of the things that Bo said in that lecture, and it was an 8-hour lecture on one of the Cisco networkers, I believe back in 2004, 2006, one of those, but I think it was 2005. He said, dense multicast is very good and you should run it in your network if you don't like to sleep. If you like meltdowns in your network and you like troubleshooting in the middle of the night, run dense mode multicast. It will provide you with endless entertainment. That stuck with me. Now, what's the problem with dense mode multicast? Well, the problem with dense mode multicast, of course, is this flood and prune and flood and prune. What if you had multi-gigabit traffic coming from the source? That means that you're going to flood throughout your network multiple gigabits of traffic and deliver them where they are not actually needed to be. So this is dense mode multicast. Now, technically speaking, dense mode multicast is not explicitly mentioned in the CCIE routing and switching blueprint, but there are some technologies that actually rely on dense mode functionality to work that are explicitly mentioned. So even though they don't say dense mode is there, you actually need to know how it works in order to understand those some other technologies. But also, in order to understand why we have the solutions in place that we do have now to actually solve this problem, we need to understand what the problem originally was. Let's take a look at how we can actually solve this problem without the flooding. Well, one of the major problems that we actually have, the thing that needs solving here, is when we have the source that is actually transmitting the traffic, and when we have the client here. The problem that needs solving is how do sources find out about the clients? How do we get the traffic from source to client without flooding it everywhere? How do we put them together? Now, this is where the concept of a rendezvous point, and I don't even want to begin spelling that, so I'm just going to say RP. Unfortunately, I don't speak French, and that's a French word. So the rendezvous point is a place, a common agreed place where clients can meet multicast sources. That's pretty much what it needs to be, but the emphasis here is a common and agreed place. Now, that means that somehow these routers in the network need to agree which one of them is going to be the rendezvous point, and everyone else in the network needs to agree about that same thing. So it's not only that they have a decision, oh, that's going to be the rendezvous point. It needs to be the same in the whole network for the multicast to operate. Now, how the routers are actually going to learn this information is a problem in itself, and I am going to explain that later on. Again, it's a chicken and the egg situation. So now I'm going to work on the assumption that these routers here in our network agree which one of them is the rendezvous point, but I'm not necessarily going to explain how that happened. I'm going to explain that later on. So for now, the only thing that we care about is that they agree that one of them is the rendezvous point. Now, but which one of them should be a rendezvous point? When I usually ask the question about which router in our network should be the rendezvous point, the usual answer that I get is R5. Now, why R5? And the answer that I always get from my students is because it's centrally located. Now, this is where I'm going to pretend for a moment that I'm not a CCIE instructor. Now, if you are in your network tasked to implement IP multicast routing, placing rendezvous point in the central location of your network may or may not be a good idea. Now, if all your sources were grouped in one location, and all your clients were grouped behind this location here, this would probably be the worst place where you want to place your rendezvous point. The best place to place your rendezvous point in that case would actually be for R1 to be the rendezvous point. Now, if you had sources that are distributed all over your network and all your clients were actually here, in that case, a good place for rendezvous point might actually be R10. Now, if you didn't know where your sources are going to be, and you didn't know where your clients are going to be, in that case, a good, nice central location actually makes sense. So these are just some very, very rough guidelines where to place the rendezvous point. But R5 as a generic answer, oh, because it's bang in the middle of our network, is not necessarily a good answer. Now, in the CCIE lab, so I'm putting back my CCIE instructor hat, in the CCIE lab, you are probably not going to be asked to make this particular decision. They're going to either tell you, put the rendezvous point wherever you like, in which case you choose, but they're not going to expect you to choose the best possible location, just some that works, or they're simply going to tell you that router there should be the rendezvous point. Now, in my example here, in order to illustrate a couple of things, I would like my rendezvous point not to be a device directly connected to sources or clients, and I would not like this to be a device directly connected to the device that is directly connected to sources or clients. Which basically means, in my example here, I really don't want to use R1 as the rendezvous point or R10, but I also don't want to use R4, R5, R2, or R9, R8, or R7, which really leaves me just two choices here. It can be either R3 or R6. Now, for the reasons that are really not relevant, I'm here going to use R6 as my rendezvous point. So I'm going to mark it here as the rendezvous point. So this is now my rendezvous point. So let me just write that down. So R6 is going to be the rendezvous point in my network. Now again, just a reminder, source S is transmitting the traffic which creates S, G state on R1, and there is client C here that requests star, G. So now let's see what happens. Now this is an ideal case in the network when we actually have both the source active and the client active at the same time. But as I said, this is an ideal case and it doesn't always happen. So what I'm going to explore first is what happens in our network when we actually don't have a client. So this here has not happened and the client does not exist. Which reminds me of a quote from a movie, Hunt for Red October, this never happened and I was never here. So if you know the movie, you know what I'm talking about. So here, what we're going to do is, there is no this client, so I'm just going to turn this to white. And this is the situation. So what happens when the source starts transmitting the traffic to our R1? Now, this creates the state on R1. The next thing that happens here is R1 is going to attempt to take all this multicast traffic, all this stuff here. So let me just use this here. All the multicast traffic as it is arriving, it is going to try and put it in sort of a IP tunnel. It's going to try to encapsulate it as unicast and send this as a unicast message to R5. R6. Now this message here is something that we call register message. Now this register message basically says I have an active source. Now mind you, this unicast traffic may actually take the actual path it takes. So let's draw this as a full line here. But the actual path that this multicast traffic takes could be, for example, this one here. Now mind you, because this is unicast traffic, this does not create any state on R2 or R3. So this unicast traffic is just sent as unicast traffic, that not affecting R2 and R3 in any way, other than that they actually have to transmit this traffic. And mind you, no other routers here are aware of anything of the sort happening. Now, when RP receives this traffic, this is actually going to create on RP, it is going to create S, G state, which tells RP that there is an active source that actually transmits in our network. Now mind you, as I said, and I will repeat this again, this is not one packet, this is not two packets, this is not 15 packets. This is R1 attempting to do this at the rate of arrival traffic. So if this is here 5 kilobits per second, R1 is going to try to do this at 5 kilobits per second. If this is 5 gigabits per second, R1 is going to try to do this at 5 gigs per second. Now, this is why, for example, an idea that if my clients are all behind, if my clients are all over the place and this is where my sources are, it makes sense to make this a rendezvous point, because then this unicast traffic will not be sent to a central location. We will be basically registering to ourselves, not consuming any external bandwidth. Now, in this case, this is the RP, so this traffic is being sent constantly as it's arriving. Now, as I said, unicast traffic goes this way, and this creates S, G state on RP. Now, what happens next is RP, if it doesn't know about any routers that might have clients, or it doesn't have any locally connected clients itself, is going to, as the result of this received message, going to respond back with message which is called register stop message. So register message was number 1 that was sent, and register stop is number 2 message that gets stopped. Now, when R1 actually receives a register stop message, it is going to stop sending this traffic. So after that register stop has been received, R1 basically starts dropping this multicast traffic. But take a look at what happens on R6. Now, R6 and no other router in our network here knows that there is an actual active source S somewhere in the network. Keep in mind that information about that the traffic originally came from R1 is irrelevant. It came from source S. Now, let's say that nothing else happens in the network, so there is no client in our network. This situation is going to stay like this for 3 minutes. After 3 minutes, what's going to happen is this. R1 is actually going to re-register with our source, and our R6 is going to send back source, is going to send back stop. So after 3 minutes. If our source is still transmitting, if the source stops transmitting the traffic, what's going to happen? The S(G) is going to expire on R1, it's going to expire on R6, and there is not going to be any trace of it. But as long as the source is transmitting, there is going to be this register stop, which is very similar to that flood prune that we had in dense mode multicast. But keep in mind that with this approach, there are only 2 routers affected by this. No other routers in the network are actually affected by this other than R1 and R6, and maybe these transit routers that are sending just a single unicast stream. But none of the other routers are actually going to get this traffic. So let's see now what happens when the source actually connects to the network. So now this is the state, and now the source has actually connected to the network. Sorry, not the source, but the client connects to the network. So client now sends that it is interested in receiving traffic sent by anyone to this group. So it creates *G state on R10. Now, R10 here looks at its own multicast state table, multicast routing table, and asks a question. Do I have any sources that are transmitting to this network? The answer is no. I don't have any sources. But I know who might know about the source. So this is where we go back to the situation that R10 and every other router in the network must agree that R6 is the rendezvous point. So R10 now says, I don't know about the source, but I might know who does. So it looks at its unicast routing table, and it says, okay, this here is the best way to reach the source, to reach the rendezvous point. And let's say that this interface here on R8 is the best way to reach the rendezvous point. So out of this interface, if it was enabled for PIM, R10 sends out *G join, asking R8 to send it the traffic for this group. Now, R8 now looks in its own table. Do I know about the sources for this group? No. So if it doesn't know, then it knows who might know. Again, R8 needs to agree that R6 is rendezvous point and sends the join towards the rendezvous point. Now, rendezvous point now knows that there is an interested client here to receive this traffic. Now, this green line here, so this path here, is something in multicast. These multicast paths, the traffic that multicast path will take, are called trees. This is something that we called a shared tree. Now, why is it called a shared tree? Well, it's called a shared tree because regardless who the source is or where the source is, the root of this tree is going to be rendezvous point. So now rendezvous point adds this interface into something that is called outgoing interface list on itself. And this outgoing interface list now means that if I receive traffic sent to this group from whatever source, I'm going to send it down this path. But now rendezvous point doesn't actually have the traffic. It just knows where the traffic is. So rendezvous point now looks, what is the best way for me to reach the source? Now, let's say that the best way for rendezvous point to reach the source is this interface here, and that on R2, this is the best interface to reach the source. So these are the RPF interfaces here. So RP now sends on this interface here, sends out S, G join. Now, this S, G join now arrives to R2. Does R2 know who the source is? If your answer to this hypothetical question was no, think again. It does know who the source is because R6 just told it who the source is. Because it sent an explicit join for the traffic going from a particular source to a particular group. So now R2 says, oh, okay, I'm just going to send this join out of my best interface towards the source. Again, R1 doesn't actually figure here. It's the source address that matters. Now, R1 that actually does have a copy of traffic arriving here says, oh, look, I actually do have an interested party. And it adds this interface to its outgoing interface list. So it no longer blocks this traffic here. So the traffic is no longer blocked. It will still be blocked here, and it will be still blocked here, but it will now send this multicast traffic down this tree here. Now, this red tree from R6 towards source is something that in multicast we call source tree. So this source tree here means that the root of the tree is the actual source. So this was built directly to the source. So if we had a different source, S1, behind R4, there would be a different tree that goes here that might deliver traffic over this shared tree. So in this part here, in the green part, we don't care who the source is, and the root is the rendezvous point. But in this red tree here, we actually do care who the source is, because this is a source tree. This is the root of our tree. The traffic will be flowing from this source onwards. Now, when this traffic arrives to R6, R6 is now going to forward this traffic as multicast traffic down this tree here. And the traffic is now delivered to our client. Now, but there is a problem with this approach. Now, the problem with this approach is that, let's say that our R10 here had the best route to reach the source out of this interface here. Now, when this traffic arrives from this green tree, isn't this traffic that has the source IP address of S, isn't it going to fail the RPF here? Well, the answer is no. Because if the only thing that we have is star, G, R10 knows the traffic will be arriving on the interface that is closest not necessarily to the source, but closest to the rendezvous point. But what R10 can do now is it can start building its own tree, because now R10 knows who the source is, because arriving traffic here told it who the source is. So now R10 can actually start building its own source tree. So now R1 is actually going to be sending the traffic. Will this work actually? Nope, I clicked on the wrong thing. I'm trying to delete these tiny little ones here. So now R1 is actually going to send a copy of traffic down this tree as well. Now, when this happens, R10 is now receiving two copies of traffic, one from the shared tree and one from the source tree. So at this point in time, R10 is actually going to start dropping this traffic and deliver this traffic to the client. Now, client here may be affected just a little bit. It might get some duplicate packets, it might miss a packet or two, but this is something that in multicast, unfortunately, is fact of life. The clients need to be able to handle this loss of traffic or duplication of traffic. So if in production environment you're actually implementing IP multicast and you have application developers that come to you and says, yeah, your network is sending me duplicate packets, fix it. You tell them, yeah, how about reading the RFC and figure out how multicast works. Now, that particular approach may not actually work, but you get the idea. I'm a confrontational person. Now, what happens next is very interesting. So now R10 is getting these 2 copies of traffic while dropping this traffic here. So what R10 is going to do next is actually going to send out prune message towards R8, and R8, having no other clients, is going to send the prune message to R6. Now R6, having no other clients, is also going to prune this path here. So what we are going to end up with, really, now in our network, after all this is said and done, is source transmitting the traffic, R1 having S, G state, R6 having S, G state, R10 having S, G state, client getting the traffic, and R7 and R4 having S, G states, and actually delivering the traffic over the most optimum path to the client. So this is now the distribution tree that we have. Now, R6 still knows, and there is still that refresher that goes on from R1 to R6 every 3 minutes. But other routers here that were delivering the traffic before, that were delivering the traffic in this example here, are no longer actually using this traffic. Okay, so that was an example of the network when we actually have a source that is transmitting. But what happens when we have a network in which we don't actually have a source transmitting, but there is a client interested in receiving the traffic? So let's mask this out now. So I'm just going to mask this one out and see what happens in our network when we actually have a client that exists, but there is no source that transmits. Now, the client is going to send IGMP join for star, G. Now, this is, of course, going to create the status on R10, the same star, G. Now, R10 is going to look at its interfaces, which is the best path to reach the rendezvous point, and it's going to send out star, G join out of this interface. Now, R9 is going to do the same thing, and this creates the state on R6. So R6 now does actually have a state. It does have an outgoing interface. So this is now added to the outgoing interface list. And this state here is unfortunately going to be maintained as long as the client wishes to receive the traffic. So R9 is now unfortunate casualty of not having the source in the network. Now, let's see what happens when the source actually shows up in the network. So the source, being the source, what it does, it transmits the traffic. This creates S, G state on R1, and this state gets created. Now, R1 at this point is going to send its own register message. So this is unicast register. Towards R6. Now, this creates S, G state on R6, and now 2 things actually happen simultaneously. One thing that happens is that this traffic here that is arriving as unicast is now going to be decapsulated and sent towards R10, down this shared tree. So this is the reason why this register message here is the actual traffic being sent. So this is not just a single message. We are actually going to be sending the actual traffic down this path. So at this point here, what R6 is going to do is it's going to start building its own tree. So it's going to say here, join S, G. R2 is going to send S, G. So now what R1 is going to be doing, on top of this unicast message going down, it's actually going to be sending multicast down this path. Now, when R6 actually receives this multicast traffic, at this point in time, it is actually going to send back to R1 the stop message. And instead of forwarding this this unicast traffic here, this multicast traffic arriving is going to be sent down this tree. Now, what happens next on R10 is going to be that switch over to the shared tree that happens by default, but there is this slight difference in behavior between what happens when we actually do have a client and the server on the network, and what happens when the client is there but there is no source, when the client just wants to receive the traffic. You can see that there is slight difference in behavior on R6 between this example and the previous example that we did. So this is really how sparse mode in a very, very broad terms. So this is sparse mode operates. Now, but all these things relied on the fact that all of my routers here knew who the rendezvous point is. So how do routers know who the rendezvous point is? Well, that is the problem, as I said, in itself. So we need to figure out how could they learn who the rendezvous point is. So rendezvous point configuration, RP configuration, in the network can be accomplished using three methods. One is static, the other one is auto RP, and the third one is using BSR, or the bootstrap router. Now, when you are configuring RP as the static on every single router in the network, what you need to do is IPPIM RP address and then you need to specify the RP. When you are configuring auto RP, what we need to do is we need to configure two roles in the network. One is we need to configure the candidate RP, and we need to configure a device or devices to be mapping agent. Now, when we are configuring BSR, we again have to configure two things. One is we need to configure RP candidates, and we need to configure BSR candidates. So let me explain how this works. So this one here is relatively straightforward. So this is simply what you would have to do on every single device in your network. But with auto RP, let's see how auto RP works. The first step is candidate RPs send multicast announcements and this is done in dense mode. That they exist. Mapping agents receive candidate messages and decide which one will be the RP, highest IP address wins, then mapping agents multicast the decision in dense mode to everyone else. So there are two groups, two multicast groups that are in use by AutoRP. As I mentioned, they are 224.01.39 and 224.01.40. Now, one of these groups is going to be used and joined only by mapping agents, and the other group is by default joined by all other Cisco routers. Now, if you can't remember which one is which, despair not, because you can always ask iOS about it. So this is what I'm going to do. I'm just going to go to one of my routers, going to just add one IP address on it, so interface loopback 0 IP address, and I'm going to say IP multicast routing. So if I do show IP mroute, I will see, okay, maybe I need to actually enable PIM on one of the interfaces, so let me do that. Interface loopback 0 IP PIM sparse dense, do show IP mroute. Now, I will see here that 224.01.40 is the group that I have joined, which tells me that this is going to be joined by every router and this here is going to be joined by only mapping agents. Because by default, Cisco routers are all going to listen for updates from mapping agents. So we are going to say here that this is going to be sent to 224.01.40, and this one here, that when candidate RP send multicast announcements in dense mode that they exist, this is actually sent to 224.01.39. So only mapping agents will actually join this group, and this is joined by all other Cisco routers. Now, the problem here is, obviously with AutoRP, is that it requires multicast to work. So it's kind of a chicken and the egg. We need RP for multicast to work, but we are distributing information about the RP using IP multicast. But remember, we need multicast only for sparse mode. But these announcements here are actually sent in dense mode. Now, in Cisco iOS, interfaces can operate in three multicast modes. They can operate in dense mode, they can operate in sparse mode, and they can operate in something that is called sparse dense mode. Now, when the traffic arrives on an interface that operates in dense mode, traffic is flooded. If it passes RPF, so we say that RPF must succeed for the following to actually happen. So traffic is flooded if we have dense mode. Now, if traffic arrives on an interface that operates in sparse mode, forward only on those interfaces with downstream clients. Also, that's just one thing. The other requirement is RP must be known. If not, traffic is dropped. So, if you don't have downstream clients, traffic will be dropped. If you have traffic clients, if you have downstream clients, the traffic will not be forwarded if the RP for that group is not known. Now, sparse dense sort of sits in between those. If RP is not known, operate in dense mode. If RP is known, operate in sparse mode. So basically, if we don't know the RP, the behavior of sparse dense mode will be this. And if we do know about the RP, the operation of sparse dense mode will be this. So one of the prerequisites for running AutoRP is to actually run in sparse dense mode. Now, in the lab, you could be asked to use AutoRP with sparse dense mode. So, in sparse mode only. So for AutoRP here, I'm just going to say that it needs sparse dense mode. But what if they ask you to run AutoRP in sparse mode only? Now, if you are asked to run in sparse mode only, you can configure the global command, which is IPExpert AutoRP listener, which basically forces these groups here to always operate in dense mode. Regardless of the interface configuration, if you configure IPExpert AutoRP listener, basically you're forcing these two groups to always operate in dense mode, even though on the interface itself you might have actually configured, sparse mode only. But generally speaking, for AutoRP, the wisest idea, the wisest decision would be to run the network in sparse dense mode. But if you are restricted to sparse mode only, you can still make it work if you are running in sparse mode with that AutoRP listener. Now, let's take a look at the BSR. Now, BSR operates in very, very similar fashion to AutoRP. You first configure candidate RPs, or I should say RP candidates. Who are then staying silent. So they are staying silent. At this point, nothing happens. Number 2, configure BSR candidates. What's going to happen at that point is they are going to start sending BSR messages to 224.0.0.13. I believe it's 13, which is the address of all PIM routers. Now, keep in mind that this here is link local. So these messages are never routed. Messages, so this is next step. Messages are flooded hop by hop by all PIM routers, all multicast routers. RP candidates on hearing from BSR unicast candidacy to BSR. BSR then includes RP candidates in next update. Now, if we take a look at this behavior, it looks very, very similar to the one from AutoRP, with one significant difference. All messages here are actually flooded throughout the network. None of these messages are actually routed through the network, which means when you are running BSR, you don't have the need for, no need for dense mode. So this can operate in sparse mode natively. It's designed for sparse mode. But more important thing is flooding is control plane function. Which means, significant thing, it can be debugged. Now, why is this significant? Because for AutoRP, the actual messages here are routed through our network. They are sent to a network, to a destination that is routable. This is not a link local address. These are globally routable addresses, which means when they arrive on a router that, let's say, might be using distributed forwarding, so it has a line card with a copy of Ceph. When a message arrives on this interface and it goes out of that interface, it may happen before the control plane on the router can actually say, oh no, I didn't actually want it to go out of that interface. You cannot control AutoRP using control plane functions. You can't say, don't send AutoRP there. You actually have to control it inline, in traffic path, using the multicast scoping, which is basically controlling how far messages go out based on the TTL, or you need to use the access list, or you actually need to examine the traffic that flows through the router there and say, okay, this multicast groups I don't want to send out and these I don't want to receive. It's really complex controlling where you want to send AutoRP out of. Now, when it comes to BSR, because this is a control plane function, this is happening hop by hop, because this address here is link local. So let me just circle that in blue because that's related to that blue statement there. This is hop by hop sent. That means that I can simply tell router, out of this interface, don't send out BSR. So it's easy to control where BSR messages go out with IPPIM BSR border command. But even more importantly, you can say debug IPPIM BSR, and what you are going to have with that debug is messages as they are arriving and as they are being regenerated. Now, even though the messages are actually flooded, and I'm going to write this down here in red, they are still subject to RPF checks. Which is important because if you can actually debug BSR in a control plane, you can see whether these messages are failing or not failing the RPF. And RPF failure is going to be the biggest challenge in the lab. How to find out where the RPF failure is and how you actually correct the RPF failure. But I will get to that in a moment. Now, the next thing here is, again, let's go back to the three methods for configuring AutoRP. We have BSR, we have AutoRP, and we have static. Now, this is the order of preference in iOS. BSR and AutoRP will be preferred over static. So if you have static configured and you have BSR and AutoRP, this will be the order. The static will be less preferred than dynamically configured information. Now, if you want to reverse the order, if you want the static to win over BSR and AutoRP, you need, not BRS, BSR, Marco. If you want static to win over AutoRP, you need to do IP PIM RP address override. Now, this will cause static to be more preferred over dynamically learned information. Now, the important thing to understand that between BSR and AutoRP, there is no tiebreaker. It will be the last one learned. So this is something that you should maybe try to avoid. So between these two, there is no tiebreaker. It will be the last information you learned. So it's basically a squirrel principle. If you hear from BSR, you're going to use BSR. If you hear from AutoRP, you're going to use AutoRP, and then you're going to be jumping back and forth. Hopefully they are sending you the same information, but if they're not sending you the same information, you might actually be in trouble in your lab.